focus today on the PLC Open motion control functions, and also show the CODESYS SoftMotion that implements these PLC Open motion control functions and extends it with many other functionality. But for today, of course, about motion control, we could easily spend several days, but the time is limited, and I see I have to catch up some minutes. However, so we will focus on the PLC Open motion control function, and maybe for another occasion we can extend this and have a detailed view on the robotics, for example, or on the CNC solution. Well, let's start with the motivation. The PLC Open started about 25 years ago to generate a standard paper how motion and logic control can be integrated in one tool or in one system. And before they did so, these were two separate worlds. You can say there was a PLC controlling the logic, and there was another controller controlling motion, controlling axis. Those two worlds were typically provided by different suppliers. So you had different engineering tools. You had communication for synchronization between those two controllers, and of course this was expensive. It needed resources. The engineering took place in two different tools. You needed export for each tool, so this was quite complicated. And then people started to integrate both systems, both kernels on one hardware. So this was a next evolution step, let's say. Still, there were some drawbacks in this. The engineering was still with two different tools, and the synchronization communication was not so easy. But triggered by this PLC Open motion control activity, people started to really integrate these two worlds in one system, as we did from the start. So we started in about the same time to implement CODESYS SoftMotion. It was about 22 years ago when we did this, and we started from the scratch to implement the motion inside the PLC. So to have one tool, one system, one engineering tool that allowed to write an application for logic and motion control at the same time, without the need of complicated synchronization or communication between the two worlds. Now, I would want to show you what the PLC Open motion control is like. First of all, let's have a look on the PLC Open organization. I don't know if you're familiar with that. The PLC Open organization tries to enhance the efficiency and automation through open standards. So its members are typically suppliers of the automation, or users that, like machine builders or plant builders, that that have to write applications. Its headquarters is in the Netherlands. Managing director is Elko van der Waal, and there are several supporting offices in the United States. One in the United States, one in Japan, one in China, and in Korea. And they focus on the technical specifications around this IEC 61131 programming language collection standard, and that also CODESYS is implementing. And they try to reduce the costs and make the industrial engineering more efficient. Yeah, a very important outcome are standardized libraries. There are several technical committees that work on these libraries, and there are experts from different member companies that come together, work together, and discuss together in order to define standardized libraries from different fields. So motion control is only one of these. There's also for safety function blocks, there's for import and export, and many others. If you are interested in details, I would like to invite you to go to the www.plcopen.org web page, where you can also download the specifications and also see the certified products that follow these specifications. About the motion control standard, and there were several parts, several different papers that were published. The first one, as mentioned, was started about 25 years ago, and the first version was released in 2001, so about 20 years ago. It was about the function block for motion control, so the single axis function blocks, the simple ones. And about 5 years later, there was an extension published following the same field of application, but with some new functions that were missing in part 1. And these two parts, they were finally merged in 2011, I guess, in a version 2.0. In addition, there is a user guideline, part 3, that explains how these function blocks can be used and show some examples, some use cases. And starting from 2011, there was the coordinated motion, part 4. This is for a different field of applications like robots and CNC. Our product, CODESYS SoftMotion, implements also these part 4 function blocks. Although today, as I mentioned, we will focus on the part 1 and 2, and keep the more complicated stuff for the next time. And then we have part 5. These are homing procedures. This is not often implemented, so it doesn't have the relevance like the other standards, because the homing is typically implemented inside the servo drives. And this standard would allow to combine single homing steps and program it in the PLC, but as it is typically configured and not programmed, this is not implemented that often. And there's another standard called another part, part 6, the fluid power extensions, basically single axis function blocks like from part 1, but dedicated to the special needs of the fluid power. Well, the target of the PLC Open was to define a paper that allowed all companies to keep their existing products, but to give a kind of a shell that allows the users to understand how these products work, without needing to learn or to get trained on each system that they are using. So the focus was not 100% standardization. This is, I think it's an illusion. So to reach 100% portability is not possible, or it is possible for sure, but practically it wasn't possible because all the vendors had some special functions they wanted to keep, and then therefore the PLC Open said, okay, our target is not to have the 100% standardization, but at least, and this is from my point of view really a huge achievement, they wanted to define a standard that everybody, all the vendors, could implement, and to allow, as a consequence, to allow the users to understand two systems that are following the standard very easily, because they have the same patterns, they have the same interfaces, they behave in the same way. The focus didn't lie on 100% complete functionality, nor on 100% performance, but the working area is what you see here in this ellipse inside the triangle. And I think 20 years later, I can say that it really was a huge achievement, and brings a lot of benefit and is very popular. The basic concept of the PLC Open function blocks is, and this is also, I think it was invented by this group, what we call a behavior model, a common behavior model. We call it in the CODESYS libraries. We are reusing this pattern for many application libraries. And this pattern consists of two basic patterns, let's say the execute done, busy active command aborted error pattern, and the enable and valid error pattern. The execute pattern is used to start commands, typically with a defined end. So it is edge triggered. That means when a rising edge on the execute is applied, the function block starts its action. Here in this example, I have the move relative function block. You see that it has some parameters. It has an axis, so that the system knows which axis we want to move. And it is started with a rising edge on the execute. And then it has several outputs, the done outputs indicating that the command has been executed completely. The busy and active output, they are very similar, indicating that the function block is still doing or preparing to do something. The command aborted output, that indicates that the action was interrupted by another function block. And then the error and error ID output that tells us if something went wrong. Here on the right side, you see an example of 3 function blocks that have been programmed together. So the first function block here is started with a start signal. You see it here on the trace. When this first execute is set, then you see that the active output becomes true because the function block is starting the movement. And when the movement is finished, it sets the first done output. And in the way it is programmed here in this example, you see that it triggers the second function block, the execute of the second function block. I don't see, can you see my mouse?
Yes, we can see it.
Perfect, thank you. It's an important feedback for me because I'm trying to indicate where to look to. Okay, so when the done is set, then we trigger the execute of the second function block, and which becomes active, and finally is done. So the third function block, there we have a different situation. It doesn't start immediately because we have this end block between, and we have to wait until in 13 becomes true. When in 13 is true, then execute becomes true as well, and the function block starts, becomes active. And in this example, it never reaches done because there is an error. So it indicates with an error function, with an error output, that something went wrong. So this is the basic principle of this execute and done pattern. And this example doesn't show what happens if the execute is set before the done appears. And this is something I want to show you later. This would cause the first function block to stop its action and to indicate that it was aborted. So it will set the command aborted. And the second function block would, in this case, take over the control of the access. Alternative to this pattern, there's another pattern that is used for function blocks that don't have let's say this command-like function, but that work without a defined end, and they are level triggered. And this is indicated with an enable input. And when the enable input is true, then it means that the function block starts its action, and as soon as possible, it will set the valid output and the values that it has collected. Like the read actual position function block is following this pattern. It just gives back the actual position of the axis. Okay, so this about the commanding of or of issuing commands from the application. And another important element of the PLC Open specification is the axis ref state machine. Every axis in the system follows this state machine. You see the graph here, and you see also the transitions between the graphs. They are not explained in detail here in my presentation, but you can see them in the PLC Open document. You can download it from the PLC Open org page, and then you can check it in detail. Typically, when the application is started, the axis is in a disabled state. And then you have to transfer it in the standstill state by putting power on it. So there's a power function block that puts the power stage to true, enables the power stage, and releases any soft stopping or soft blocking of the axis. And then the axis is in standstill state. And then you can execute a homing. This is a separate state where the axis finds its own reference. And after this is done, you can start to move the axis. And the moving, there's not just one moving state, but there are 4 states in the end, 4 states for it. One is the discrete motion state. So these states are used or introduced, have been introduced to distinguish between the type of motion that is executed. The discrete motion state means that the movement has a defined end. Typical example is a move absolute command. Move absolute means we want to move the axis to a certain position, and there it should stop. So we have a defined stop, defined end, and therefore this is a discrete motion. In contrast to this, we have the continuous motion, where we issue a command, and this command runs without end. So like move velocity, when we say, okay, axis move with a certain velocity, it will run endlessly, or let's say until we interrupt it with another movement. This is the continuous motion. And then we have the synchronized motion. This indicates that this axis is bound to another axis, to a master axis that controls the movement somehow, like in case of the gear in function block, we have the master that turns with a certain speed and the slave following exactly this speed. So synchronizing its speed on the master speed, synchronized motion. And as a special case of the discrete motion, we have the stopping, and it has they have defined a separate state for it, because the stopping cannot be interrupted. There is no way to interrupt a stopping except with an error. So in case this is node 1, would mean every step can be transferred into an error stop state, because when an error occurs, the axis automatically goes to error stop, and then after the error is reset, can be transferred to standstill or to disable, depending on the situation. So this is the state machine of PLC Open, and all the axes follow this state machine. Now I would like to introduce several typical function blocks to you. The standard contains, I guess, about 30 standardized function blocks. We don't have the time to see all of them in detail, but I selected the most important ones from my point of view. And let's start with the administrative function blocks, like the MC power. This function block is used, I named it already, it's used to control the power stage of the axis. So you say you enable it, and then you have the possibility, in our system at least, to control the regulator on and the drive start flag. These are controlling the power and a soft stop of the axis. And when the power is applied and the axis is ready to move, you will see here the status output of the axis that allows you to issue new or really movements on it. Alternatively to you can get as an alternative to read the status from the axis, you can also apply the MC read status function block. And this function block gives you detailed information. First of all, about the state in which the axis is. Like here we have the arrow stop, stopping, disabled, standstill, discrete motions, these different kind of motion types, but also if the axis is running at constant speed, or if it's currently accelerating, decelerating, all this kind of information you find in this read status function block. And then there is another useful function block, the MC set position. It allows you to set, as the name says, set the position of this axis. So it's kind of a soft homing. You can specify the current position of the axis without moving it. So if you say, okay, at this position I want to have position 0, then you can shift the scale by issuing this command, and then the axis actual position will be 0. Yeah, well, and then is there read axis arrow function block that gives you information about an error that could occur inside the axis. That might be a following error, that might be a over temperature or under power error. Get here an error ID. And if you have solved the problem, you can apply the MC reset function block that is resetting the state of the axis into standstill, and then you can use it with the movement function blocks again. Now I would like to come to this segment, the single axis movements. First of all, the MC home function block, issuing a homing on the axis. As mentioned before, typically the systems have within the configuration of the axis the possibility to also specify what homing procedures should be executed, and then on the side of the function block it's just triggering it and starting it, and maybe specifying the position and waiting for the done. And after we have homed the axis, we can start to move it. Of course, we don't have to home every axis. If you have an absolute encoder on the axis, it's not necessary to home it. But of course, it's for the other types, it's necessary. And then we have this move absolute function block, and that allows us to specify a position where we want to move this axis to. We need other parameters like the velocity, the acceleration, deceleration, and even the jerk. And in case of modulo axis, we can also define the direction, because then we have, of course, always two possibilities to reach a position, in positive direction, negative direction, or even in shortest direction or in fastest direction. So there are different modes to execute this, and all the function blocks have also a buffer mode. A buffer mode has been introduced in order to allow to start several movements without immediately interrupting them, but you can also stack these movements, and this is done with the buffer mode. And the outputs, you know already, they are very similar here between the move relative and the move absolute function blocks. These are the ones from the pattern that I explained before. So no specific other output. Let's see the move relative function block. That is very similar. The only difference is that it's not expecting a position, but a distance as an input. So relative to the position where the axis is when we start this movement, the axis is moved. And also you will see there is no direction, because the direction is implicitly defined with the sign of this distance. If it's positive, then it's positive direction. If negative, it's negative direction. Then we have the move velocity function block. This is, I explained it already. You can specify a velocity, and when you start it, there will be a ramp in phase that takes into account the acceleration, deceleration, and jerk. And then the axis should reach this defined velocity, and it will be kept moving with this velocity until it is interrupted by any other function block. You see that it's not, this is an exception, it's not indicating a done, because it's not done in this sense, but it's moving endlessly, so it only has an in velocity output that says that the axis has reached the specified velocity. And then we have the halt and the stop function blocks. They have more or less the same functionality. They stop the axis to velocity 0, to standstill. The difference is that MC halt can be interrupted by other function blocks, whereas MC stop not. MC stop is blocking as long as the execute is true on MC stop. The axis cannot move. Whereas MC halt, for example, you can start it, but you can interrupt this stopping or halting by issuing another function block. Let's see another category. These are the master-slave movements. 3 examples of this category. One is the MC gear in, used to have a certain ratio between the velocity of the master and the velocity of the slave. So the master is just used as an input. It is not influenced by this function block, but the slave, this function block takes control over the slave, starts it, and according to the setting here, the numerator and denominator, and the speed after a ramp in phase again, the speed of the slave will follow the speed of the master, taking into account the ratio, of course. And the phasing function block is issuing a phase shift between them, realizing a phase shift between master and slave. So you define this phase shift here. The velocity, acceleration, deceleration are only for ramp in. And then when both axes have the same velocity, the function block takes care of keeping the phase shift identically. And otherwise, they are synchronized. The chem-in function block is a more complicated one, or not really complicated, but a little bit more complicated. It allows you to realize chem tables. You know that chem tables are used often in packaging applications, labeling, cutting, and so on, where again you have a master-slave relation, but it's not like here with the gear in, where you have a very linear relation between those two, but where you have a more flexible one, where you want to define the function between the position of the slave and the master with more points and more complex segments. And this function block helps you to realize this. It starts a chem table on a master, on a slave, depending on the master. You have, for the ramping in phase, you have several parameters again here, and also you can define an offset of master and slave and a scaling here, and some start modes. So these are parameters for this function block, and then it realizes this movement of the slave depending on this chem table and the master movement. Okay, so this is about the PLC Open function blocks that I wanted to show you. And now I would like to switch to CODESYS and have some live presentation on how the function blocks are used and combined. I've prepared an empty project for you. And the first thing I need to do is I need to introduce an axis. I use a virtual drive as for the demonstration. If we have field bus devices here, like the EtherCAD or can open, we could also add real devices to the system, and you see that there will be always one slave device, and this is the axis that represents the slave device that can be used in combination with our motion control function blocks. In our case, we want to use a virtual axis. So I add this virtual axis. I remove the EtherCAD axis because I don't have it connected. And now we have this SM drive virtual, and I can start here in my program to add some boxes. I will do quite an easy example. I'll just add the power function block, and I will add, let's say, a move absolute function block. And we will use a third one, let's say a move relative function block. Okay, and what I need to do now, I have to define, I have already, or CODESYS has automatically generated instances for me of these function blocks. And now I need to tell the system on which, or to tell the function blocks on which axis they should work. And I'm just using the name from the configuration for this. So of course I could also give another name to it, but now I use the default name. And this is all I have to do for now. I could do some configuration of the axis, for example, if it's a modulo axis or if it's a finite axis. I let it like this. I could have some software limits, some error rejection, and some other settings. Not relevant for us right now. I log into my device, and then we see here our function block instances. I start, they don't do anything because the inputs are not yet set, and I can start to set the input flags to true. This will make the axis be enabled, so the status becomes true. And then I can, okay, now I could do a homing, but on a virtual axis, it doesn't make sense to make a homing, but I can start with my first movement. I could say I want to move to position 500. I specify acceleration, deceleration, and jerk. And then I trigger this movement. And you see it starts moving. And you see also here there's a busy output. And when it has reached the 500, then it sets its done output. And now if I reset this execute input, you will also see that the outputs are reset. This is also part of this common behavior model. Now I would like to show you the move relative function block. Let's say the move relative function block, we move in negative direction, and let's use a slower speed for it, so that we have the time to issue another command while it is active. You see now it starts to move in this direction with 10 units per second. And now at position 400, it should stop exactly because we started at 500 and we had a distance of -100. So now we reach 400. And now I would like to show you how this interruption of the function blocks works. I start again the move relative function block. And now while it is moving, I start the move absolute function block again. And you will see that the move relative function block becomes interrupted. It sets its command aborted output, and the move absolute function block takes control over the axis until it is done. Of course, when I reset, retrigger the execute, then the move relative function block starts again to move. And I can, of course, interrupt myself, so interrupt the same function block. And when I do so, you will see we won't reach 400 because I interrupted at, let's say, position 450 or 433, obviously. So now we reach to 333. Yeah, well, this is a very, very simple example just to show you the basic principle of these motion control function blocks, I would like to point to our online help. You'll find at help.codesys.com. You'll find a huge chapter also for the motion control function blocks. So the PLC Open function blocks you find here, and so on, and also the applications examples. This I wanted to make you aware of. There are several examples that are explained step by step, and that you could use if you're interested to get familiar with the system. Okay, that's about this short presentation, short live demo. Now let's switch back to the slides again. This was about the SoftMotion Basic. The SoftMotion Basic is a separate license. We have the SoftMotion product is divided in two sub licenses. One is the SoftMotion Basic. You can buy the SoftMotion Basic license that contains a CAM editor, this configuration of the axis, the function block libraries itself, containing, of course, the PLC Open motion control libraries, and the drive interface that realizes the communication, which is also a very important part to the servo drives. I will explain that later on. And then we have the CNC and robotics package that has a CNC editor, the axis group configuration, the PLC Open Part 4 function blocks for the robotics, and the CNC with G-code implementation to do synchronized and multi-axis control. Just to have a short view on, because I explained the CAM tables before, we have also an integrated editor into CODESYS where you can graphically design a CAM table. You see on the x-axis is the master position always, and on the y-axis you have the slave position, the slave velocity, and the slave acceleration. This is just one example of a typical CAM table where we have one part where we have constant speed and another part where we decelerate and stop. So at the master position 0, the slave has velocity 0, it means it's stopped, and then it catches up again. And between 120 and 240 degree, we have a phase of synchronity. And of course, you can modify these tables and add different points in the CAM table as you like. So this is a design tool for CAM tables. And now I would just try to I would like to tell some words about the drive interface, because it's really a very important component of the CODESYS SoftMotion. The drive interface is responsible for doing this abstraction of the axis ref and the real hardware. You have seen in our example, we use this virtual drive, but I showed you also that we can typically we use a real hardware, a real servo drive hardware, like with EtherCAD or Can Open. And you surely can imagine that there is has to be executed some action to fill this axis ref interface and to implement it, to implement drivers that really control this axis. In CODESYS, you have many servo drives already included. So we have dedicated drivers for a huge number of different drives. You can scan them on codesys.com products, SoftMotion. And these drives are really specific for these manufacturers, and we test them regularly with each release and make sure that they have a high quality and that all the PLC Open function blocks work on them without problem. And we have standard drivers following some specifications like the CAA Canon Automation 402 that can be applied on Can Open and EtherCAD drives. We have also a standard driver for EtherCAD SOE specification. The difference to the specific drivers is that this is our interpretation of the standard, and we cannot test it with all available drives on the market, and therefore there's a certain risk that it maybe does not fully work from the scratch, but there are some parameters you can set in the standard drivers to adapt it to almost any model that claims to support CAA 402 or EtherCAT SOE. Further drives and also this testing of the drives we can do on request. Yeah, we have also special drivers that close the position loop inside the controller. So when using a servo drive, the servo drive closes the loop for us, but we are also capable of doing this, and we apply this for stepper motors, where we close the loop, and also for frequency converters in retrofit applications, we can do this as well. We have the virtual axis for simulation or as virtual master, and we have an unlimited number of these. You can add as many as you like. And so the representation of each SoftMotion axis is always the same, and this has a huge benefit because it separates the application from this from this field level. That means when you have to replace one servo axis with another type manufacturer, you can still keep the application as it is, because there is this abstract interface between. And this makes it very easy to implement reusable code, reusable applications, also library functions, because you have also always this layer in between, this axis ref layer. Well, now I'll speed up a little bit, sorry. So just one word about, I mentioned it already, so the typical architecture is using a servo drive, where the servo drive does the closed loop control. And we can also use stepper drives. We need a pulse direction interface, the position control loop to compensate single steps that have been generated too much due to time jitter or to rounding effects. Or we have the position control loop that we close here in case for frequency converters that expect a set velocity as an input, and via the encoder position that we get back, we can close the loop here. No matter what kind of architecture you select or your customer select, for us it's always an abstract axis that we use in our PLC, and that makes the PLC program independent from the real hardware and the real implementation. So just a short word about the CODESYS SoftMotion Lite. There is another product that we offer in the CODESYS store. This is called CODESYS SoftMotion Lite. It's a pure library product. And in contrast to the CODESYS SoftMotion, where we control the axis very tightly by exchanging cyclically set values and actual values with the drive, and calculating the trajectory inside the controller, the CODESYS SoftMotion Lite applies another method. It sends commands to the drive that has to be intelligent in that sense, that it can execute these commands and reports when the command is finished. And therefore, the CODESYS SoftMotion requires higher computing power on the PLC or the controller. It needs also a little bit more, or definitely more, field bus bandwidth, and requires also real-time property of the system, whereas the SoftMotion Lite doesn't. Sending just a command is not even real-time demanding, and also the calculation inside the controller is of course much less than in the other case. These are benefits for the SoftMotion Lite. The drawback is that you cannot synchronize the axis. You can, of course, move more than one axis, but not in a synchronized way. You will have to command them separately. Whereas the SoftMotion having a real tight control on the axis can synchronize them very easily, and moreover, it can control them very quickly. So in the cycle, when you start a movement, you will see the first set value going out to the drive that starts the trajectory immediately. Sorry. So this is just the SoftMotion Lite is made for other field of application where you have really very simple movements and that don't have to be synchronized, and where it's not important if you really react very quickly. Well, now I'd like to come to the conclusion. The benefits of PLC Open Motion Control function blocks and CODESYS SoftMotion. The benefits of this PLC Open function blocks for sure is that there are standardized function block interfaces. Everybody that has worked already can understand how another system works with it, and then he will be familiar without a huge training effort. This is for sure a real benefit of the PLC Open motion control definitions. It also enables the user to have a good structure of his application, because these function blocks are easy to understand and help, because they're like not really object orientated, but it's really close to object orientation. How you can program with these function blocks. It's very flexible. When you change the servo drives, you don't have to change the application program. And yeah, it's flexible also in the way that there are many compatible controller hardwares available on the market, and even especially in these days where we have this shortage of available hardware. Sometimes our customers are forced to use another manufacturer's hardware because the other manufacturer is more or less sold out and doesn't have any parts anymore. And so then this is a huge benefit that you can save the application and reuse it on another target without re-engineering everything. And last but not least, the integration in CODESYS is a huge benefit. So you cannot only not just write the logic application, but also the motion application, the safety, the visualization, the field bus communication. All that stuff is integrated in one tool, and it makes it easy and consistent, and of course also cost efficient.